All right. Okay, so quick review from, I guess it would have been, what, Thursday, Friday? We were talking about trapezoidal rule. Okay, so this is, remember, this is a numerical method that we use when you can't use an analytical method. So if we're trying to find an area under a curve and you can't integrate, there is no antiderivative, then you have to just use some approximation method to approximate the area under the curve. So we've had some experience with that earlier in the year, recall. We developed the whole idea of an integral by taking sums of rectangles, right? Inscribed or circumscribed rectangles. We could call it a left sum or a right sum. Didn't really matter at that time because we were always able to take a limit as the number of rectangles went to infinity. Let's everybody close those up all the way, please. All right. So, we didn't have to worry about getting too accurate of a shape because we had the ability to take that limit. But that ability goes away when we can't integrate the function. We can't find an antiderivative. That also implies that you can't take that limit. And so now we have to be a little smarter about this, right? Now we have to think of a better shape, something that's going to more closely approximate the curve so we don't need so many of them, right? We want to find something that works fairly well. We want to find a balance between a shape that's going to match the curve fairly well, but is also really simple to use, so the areas are easy to calculate. And typically the shape that the conclusion we come to is trapezoid, right? So we're going to create trapezoids instead of rectangles because they match the shape fairly well, especially when the width gets small, then the trapezoids mirror the curve very well, right? Okay, and so there is another common way to do this. I guess I'll just mention it now. We're not going to do it, but there is another common way we can approach this, and that is to use a better shape, but one that's harder to calculate. This is called Simpson's rule. Like, let's say we wanted, here's an interval, and we want to match the area under that curve. Well, the trapezoidal rule is going to create a linear cap to that subinterval, right? Which is not bad, but you can see that when we draw a straight line, it does miss the curve a little bit, where the curve is particularly curvy. So what's another approach? Well, we could do something where we could do a quadratic fit on the top of that function. So we could take 3 points. We could take the end points, and we could take the midpoint of the interval, and we could use those 3 points and do a regressional fit for a quadratic function. And we could create something, in this case, it would probably look more like that, maybe. I don't know exactly what it would look like, but it's going to have a little curvature to it. And so it is going to match the curve better. What's the problem with that, obviously? You can anticipate. Yeah, it's going to be a harder area to calculate. And so although you might need fewer of those to get a good approximation, they are harder to calculate. And this is where I think the conversation gets kind of non-mathematical but interesting. And this is where we think about when you're designing software or hardware to do calculations like this, like a graphing calculator or a circuit that's going to do some onboard processing for some type of engineered device. You've got to think about what are the capacities of that chip to do calculations. Is it one that can do lots of high-speed, simple calculations like most of our chips do at this point, where they're just real linear, fast processing chips? Then you probably want to pick something where it's an easy calculation, but you're going to have to add up lots of them. Or, what's sort of the wave of the future, what you're starting to see more and more now is called parallel processing. And that's the holy grail of sort of the new wave in computer technology, is to develop processors that think independently and can be assigned independent tasks. And each processor can do more than just come up with ones and zeros. They can actually come up with more complex answers. So this is going to probably leverage the whole quantum computing movement, where with quantum computing you don't just have bits, you don't just have zeros and ones, you have qubits, you have quantum bits, which can store more information than just 0 or 1. And the processing speed could go way down, but because everything's happening in parallel, you can accomplish much more complex tasks. Like the brain, human brain, our processing speed is dismally slow, but we can multitask and we can divert our attention in along multiple pathways, and so we can think about things that are really complex that computers can't really think about very well, because we're able to channel our thinking along different parallel paths. Right now, that's difficult to do, but this has some impact on how the kinds of algorithms that we're going to design to solve these kinds of questions. It's all going to change. It's all going to change when we start to build computers that can do a better job of doing more complex tasks more slowly. Well, in that case, we're not going to assign lots of little trapezoids. We're going to assign a handful of relatively large subdivisions that are going to be able to match the curve very well. See what I'm saying? So it's just an idea. I mean, if you have any interest, and at this point you might, if you have any interest in either computer science or electrical engineering with, that's geared towards, towards computer science, if this sounds interesting to you, it's something you might want to explore a little bit as an undergrad. All right, so let's focus on the trapezoidal rule. So we're going to take the simplest area, but we're going to be able to calculate lots of them. We're going to come up with a pretty basic algorithm. And we already did this. We did this yesterday, or a few days ago. We came up with a rule, remember, that looked like this. And it came from this. I guess I better go back to the picture for just a second. When we added up all these trapezoids, remember, and we did a little bit of, we added up the area of each trapezoid, and then when we factored out the 1/2, and we factored out the delta x, and we just got this string of terms, values of the function. Remember that every interval except the first and the last double counted the height of the function for x sub 1 all the way through x sub n minus 1. But x sub 0, which we call a, and x sub n, which we might call b, those were single counted. Okay, because and if we look at the picture, the reason being that the right edge of the first trapezoid becomes the left edge of the second, right? The right edge of the second becomes the left edge of the third, and so on. But what about that first trapezoid then? Its left edge is only a left edge. It's never a right edge, right? And then the last trapezoid, its left edge is a right edge of the second to last, but its right edge, the last trapezoid's right edge, is only a right edge. It never gets to act as a left edge. And so we ended up with, double counting this interior sum, and we arrived at a pretty easy formula then. The area of the trapezoid was just, we had this coefficient out front of the sum, b minus a over 2n, right? B minus a over n, and we factored out that 1/2. So that's always going to sit out front, but then from that point forward, we're going to add up the value of the function at a and the value of the function at b, x sub n, but we have to double the sum of f of x sub 1 through f of x sub n minus 1, right? Those all get double counted. And so this is the way that formula shows up in our textbook in Larson, and it's pretty common. I think this is maybe a better way to do it, though, because this, if you only have a handful of trapezoids you're adding up, then that's fine, but rarely is that the case. Usually we're going to have a fairly large number of trapezoids we're adding up, and so we want to use sigma notation because we're going to be using technology to do this. Okay, so here's my coefficient. Here are the value of the function at a and b, and then here's this interior sum, right? We've got this 2 out front. We factored out the 2, so it's 2 times the sum of f of x sub I when we go from 1 to I minus 1. Okay, and don't lose sight. You've done so much with this in the past that I probably didn't re-derive what this means, but remember x sub I, right? The right edge of the I subinterval, if we want to think about that. We don't even really have to think about it that way anymore. X sub I is just going to be defined as a plus I delta x. It's the starting point of the area plus, we're going to move to the right, delta x I times. We're taking I steps of width delta x from the beginning, right? That's how we define x sub I, and that's what shows up in our function, okay? So let's try this. Let's try this for a small number of trapezoids and a large number of trapezoids. So how about if we do, well, here's one that we did. Let's do that one. So so let's do this guy. How about if we do, let's go ahead and pick, let's do a small number first. Let's let the number of trapezoids equal 4. Okay? And then we'll do a bigger number. We'll do like 40. Okay? So what we got to start off with our formula. What's our formula going to be? Okay, so we get the area by the trapezoidal rule is b minus a over 2n times what? Okay, f of x sub n. Now let's go ahead and figure out what x sub 1 and x sub what a, x sub 1, x sub 2, x sub 3, and x sub 4 are going to be. If n is 4, a is 0, right? B is the square root of pi over 2, kind of a weird upper limit. What's delta x going to look like? What's the definition of delta x always? B minus a over n. Good. So b minus a over n is going to equal what for us then? Square root of pi over 2 all over 4. Right. Okay. And so x sub 1, or a is just 0, isn't it? So we're going to evaluate the function. We're going to do plain old f of a, which is f of 0, plus 2 times the interior sum. So that's going to be f of x sub 1. Well, what's x sub 1? Yeah, pi over 2 over 4, right? A, which is 0, plus I, which is 1, times that. So f of square root pi over 2 over 4, okay, plus f of x sub 2, right? So what's f of x sub 2 going to be? Well, it's that times 2, right? So square root of pi halves over 4 times 2. Well, 2 over 4 is just 1 over 2, right? So this is just x sub 1, x sub 2, x sub 3 would be what? Okay. And then x sub 4 is the last one, right? So that's b. Okay. That's going to be plus f of square root of pi over 2. Good. And there's our sum, right? Notice that we're going to multiply 2 by the interior sum, by everything except the first and the last term, right? So now we're going to actually plug this into our function. Well, our function is cosine of x squared. So what's that going to become then? And b minus a over 2n, we could plug that in too. That's just going to end up being square root of pi over 2 divided by 2 times 4 is 8, right? So this term is going to become, right, there's my coefficient. What's f of 0? 1, right? Because we're taking a cosine. Remember, this is just f of x, isn't it, right here? Right, so f of 0 would be cosine of 0, which is 1, plus 2 times, what about this? What's f of pi, the square root of pi over 2 over 4? So that's going to be cosine of that whole thing squared, right? So that's going to be the cosine of, we're going to get
32.
Right, pi over 2 over 16, right? Everybody agree that's going to be pi over 32 when I square that whole thing out? Okay, plus cosine of, what's this be, pi over 8? Because I'm going to get pi halves divided by 4, 2 squared is 4, right? Plus cosine of, what are we going to get, 9 pi over 32 when I square that whole thing out. And then plus, at the end, this is just going to be pi over 2, right? What's cosine of pi over 2? 0. So that's not stuff we can do without a calculator, so we'll just plug all that into our calculator. Okay. And so we got to do our integral. So we have to go down here to functions, miscellaneous, there it is. Oops, no we don't. What am I saying? We're just going to add stuff up. So we're going to have square root of pi halves divided by 8 times I wonder if I can use the script. I guess we'll see. 1 plus 2 times, oops, cosine, oh, and I want to make sure I'm in radians mode, which I think I am. Okay. So cosine of pi 30 seconds plus, and I'll just copy and paste here from that point, pi eighths okay, does that look good? And then plus 0, which we don't have to have. Okay, so what's that give us? How come it's not giving me an answer? Okay, I think I can't use the script brackets. I think those are mean a set. So And I wonder if I can't use the square brackets. It didn't? Okay. All right, let's try. There we go. So you just have to use parentheses. Okay, so there's the area. Okay. Who knows how accurate that is? We'll talk about that in a little bit, about how we can estimate the area. Okay, so let's compare that to what we get if we calculate the area using a much larger number of trapezoids. Like, let's say we're going to use 40 trapezoids. We don't want to add those up manually, though, do we? Right? That's not going to be fun. So we'll take the same problem. Say A equals 40, then we definitely want to use the sigma notation, right? We'll use our technology's ability to add up sums quickly, right? So let's restate the trapezoidal rule with our sigma notation. So we still get what? The B minus A over 2N. Now see if you can do this without looking at your notes. So then what? A plus f of b or f of x of n. Same thing. Good. F of x sub I, right? Now let's go ahead and just write that as f of a plus I delta x, right? Because that's always what we're going to plug in for x sub I, right? Right, and we're going to sum that. I'll just erase that. And just the interior sum, just to the n minus 1 term. And then that's it, right? So now we have to know, we have to be able to plug in all this stuff, though. Well, we know what the function is. It's x cosine of x squared. We know what a and b are. So really, we're okay. Delta x, we already said was, we already calculated that last time. Only this time, n is 40, right? So delta x is going to be b minus a over 40, right? And so if we plug in all the stuff that we know then, that's going to give us square root of pi over 2 minus 0, so pi over 2 divided by 2 times 40, so it's all over 80. There's our coefficient. F of a we already said was 1, right? F of b we already said was 0. Plus 2 times the sum of, so what's a plus I delta x going to look like? 0 plus I times delta x would just be that times I, right? And we're taking the cosine of that squared, right? So cosine of I times square root of pi over 2 over 40 squared. Okay, does that make sense? You can pause there and see if there's any questions. What's I going from? 1 to 39, yeah, right, because I minus 1. Questions on that? Because that's really all we have to do, right? Now we'll let the calculator evaluate that for us. Right.
Is that the integral of what's prior to the brackets?
Right here,
Yeah.
that's square root.
No. I mean, like, what we
That?
just did was the integral of that.
Oh, up here?
No. Go to the green.
Right there?
That's the integral of it.
No, you mean because it's sigma, because with the sigma you mean? It's not, it's similar, but it's not.
Looks really similar.
It does look similar. It does look similar. We would have, when we used the rectangles, we would have come up with an expression that looked an awful lot like that, I agree. It's a little different. But the problem would have been, and this is an example of a function that has no antiderivative, and so we would have, the math gods would have foiled us if we had tried this one earlier. It wouldn't work. There's no way to write this in a way where we can take a limit. It just doesn't work. Remember, if you think back, remember all those problems we did with the rectangles. They always implicitly relied on our ability to add up a sum of like something like the sum of x squared from 1 to n, right? And we had a formula for that. There is no formula for the sum of cosine of x squared. There just, one doesn't exist. So we could never do it. Question? That's a good question. It just doesn't work. There is no, and what's bizarre about that then, what that actually also implies is that there is nothing we could differentiate to get this function, which there's a part of me that just can't believe that, because think what a derivative means. A derivative is like a slope function, right? There is no curve that is going to have a slope function like that. I mean, it just doesn't, which just seems bizarre, but it doesn't exist. There isn't one. It's hard to wrap your brain around that, but it just doesn't work. Okay, so let's throw that in the trusty calculator and see what happens.
How are we gonna do it?
We can do it. We can do it, especially in Desmos, it's even easier.
I get it.
So we'll go, let's see, we got square root, pi over 2.
Were you asking them about I?
Yeah, it's the,
You just use that or something.
Times 1 plus 2 times sum, and I think to get the sum, I wonder if I do sum, it does it, check that out. If you just type sum, it does that. That's pretty cool. So it uses n's instead of i's. I wonder if I can change that. Try it. See what happens. 1 to 39 of what? We're taking the sum of cosine of, I times, see, I'm worried this is going to, what do you think it might interpret that I as being?
Imaginary.
Yeah, I think that's what's going to happen. Okay, and then I think I have to do, right, all that squared. Okay, that looks good. Boy, it's a mess, huh? That is a squared. It just doesn't raise it very high. And then I think I need one more set of parentheses, don't I? 1, 2, 3. No, I guess I'm good. I'm good. So that's it. 0.773368. Okay. Let's see if that changes when I put an n in instead of an I. Or if it, I think it's, maybe it's smart enough to know. Whoops. Oh man. Maybe it's smart enough to know. Yeah, it was. So I can use an I. It's smart enough to know that if you use an I in that context, it's not the imaginary number. That's pretty cool. Okay. So which one's more accurate? Yeah, the 40, for sure, right? Say it again. It is. Yeah, this one's 0.773368. So do you want to see what it actually is? Because Desmos already has a program that relies on the processor in this computer to give us a good approximation. So let's just see. Okay, if I start typing out integral, it makes an integral sign. That's kind of cool. From 0 to, I'm learning all kinds of new stuff today. Yeah.
I think it's just int, the int of it, maybe.
And if you do SQRT, it makes a square root.
It's the same on the Math Excel to do backslash SQRT or backslash.
Yeah, that's pretty
Yeah.
common. Pi divided by 2. And what was it again? Cosine
Cosine x squared.
x squared. So, oh my goodness.
Oh, I think I might know why.
I got .97.
Because it might just be because of the way that the cosine x squared graphs is.
I think we must have made a mistake putting that in there because there's no way it should be.
I got .977.
Is it 5 plus or 10 times?
Oh, no. Okay, I think I see. I know what it is. I know what it is. I need an extra set of parentheses in there. This is why. Watch this.
Yeah, around the square.
Yep, around squared.
It's already got it.
That's
Yeah, now, okay, do you see that?
Yeah.
That got a little confusing. It'd be nice to use something other than parentheses. I wish you could do that, but evidently you can't. You understand, obviously the advantage of using different grouping symbols is you can see which one goes with which better. I wonder if you could like make those different, I don't know. Anyway, so
Cosine x squared.
we, you can see that we were getting fairly close, right? But it's not perfect. I mean, it's a lot closer than 4. Going from 4 to 40 made a big difference, but it's not perfect. What would we have to tweak here if we wanted to make this go out to like 400 trapezoids in our formula? See if we can just power through this one. Well, here, what would that change if we go up and look at our algorithm?
You would have to change.
Yeah, it's going to change delta x, isn't it? So we'll just make our changes in hot pink here so we can see them easily. Right, so that's going to, that's going to change delta x. That's going to become a 400, right? This is going to become 800, and that's going to go, instead of from 1 to 39, it's going to be 1 to
399.
399, yeah, right. And then this would be a 400, right? So let's just make those tweaks and see how close we get.
Can you send that page for just a second?
Yep.
You did. Calculation
I
drawing.
think that thing literally right in only a minute. Yeah, look at that. As soon as I took the picture, it switched. One single frame.
Is it a ghost?
Yeah, Cassie, he's not very
.97744.
Okay, so we changed that to 800. We said that was 399. We said that was 400. And what do we get? How close? Pretty close. So we're out to 1, 2, 3, 4, 5 decimal places. Okay. Okay, so it's an interesting question. You can't take a limit, but what we could do, this would be kind of nice. What we could do, how much time we got?
2 minutes.
Okay, I maybe have time. So what if we went back to this and we said, okay, let's just leave this as n, and in Desmos you can create a slider. This is kind of cool. So we could write this in terms of n, and then what would this be down here? Well, this would just be n. This would be n minus 1, and this would be a 2n, right? So watch this then. This is pretty cool. This is fun with math toys right here.
just n over 200.
So we'd make this 2n. We'd make this n minus 1. We'd make this n. And now we can add a slider for n. And let's let n go from, let's let it go from 10 to, actually let it go from 0 to 1,000. in steps of 100. Okay? And then we can drag, if we drag this all the way up there, look what it does. Like there's 1,000. That gets it pretty close. See?